So we're going to look at different quantized phenomena that was observed that could not be explained using classical mechanics. And so one thing that you need to know about this time frame where all these experiments were being done, this was in like the 1900s, late 1900s, early 20th century. So like 1890 to 1900. Around this time, many of the physics researchers in physics, um, they they thought they had everything figured out. All the theories were pretty tight. Could be every phenomena that they observed could be explained using existing theories, which we now call classical mechanics, which or Newtonian mechanics. And these observations were all of things in the macroscopic world. Planetary trajectory, all the types of motions could be predicted, and everything was great. They were patents on the back, but then we started doing experiments looking at the atom and looking at electrons, and what we found was that their predictions did not match their expectations based on the rules that they thought everything was following. And so what we're going to go through is a couple experiments that showed the quantization of either energy, mainly of energy in different ways. And so the first one we'll look at. So what we're going to look at is we want to know what the experiment was, the expectation of what was believed would happen, what actually happened, and why, and then sometimes the resulting theory out of that. So the first is we're going to look at is the emission of electromagnetic radiation or light from matter. And the first one we're going to look at is the atomic emission spectrum. Okay. And so what happened was we had, and I'm going to post a video that's a little bit better to give you a better visual, but we're going to have a gas in here. Let's say this is H2 gas. We're going to put it a big voltage across it, so we get it shining very bright, and that this light is then passed through a prism. And this light will then diffract into corresponding wavelengths of light. Now, what they thought was going to happen was that we were going to have a rainbow. So they thought that we were going to have some red, orange, yellow, green. So they thought that we were going to have a complete rainbow of light that was continuous. So the expectation, let's write that down, was, so the expectation, if you take any matter, not just hydrogen, any matter, and you put enough energy through it, expectation would be a continuous spectrum of light emitted from the matter. Okay. And so we would see that as a rainbow if the light was passed through a prism, which would kind of separate out all the wavelengths. Now, what they found for hydrogen was not that at all. It was not continuous. It turned out that what they actually saw was 4 bands. And so we could see that the 4 bands had, we had a red band, we had a green band, we had a blue band, and a violet band. So we had 4 bands, and that was it. And that was that. And this was for hydrogen. And so this was not what they expected. And what this showed is that if you put as much energy as you possibly could into hydrogen, what that was doing was it was exciting hydrogen to different energy levels, and those energy levels were limited to 4. And so, because it was not a continuous spectrum, the resulting theory that came out of that was that they knew that. So, resulting theory was this was the beginning of quantum theory. So there were multiple experiments led to this, but what we got was that energy. We knew that energy was proportional to the frequency. Again, we could also use wavelength. We tend to use frequency here because it's nice and linear. So we know that's proportional. And if we want to take proportionality and we want to make it an equality, we add a constant. And so the measured constant was Planck's constant. So we said that the change in energy was proportional to Planck's constant times the frequency, where Planck's constant, h, is very, very small. So this is Planck's constant. And it's equal to 6.626 times 10 to the negative 34th joules times seconds. Okay, and so we can, this equation here is showing us that the change in energy is related to the frequency. We can take the known relationship between frequency and the speed of light and wavelength, and we can put this in terms of wavelength. So delta E is equal to hc over lambda. Now, both of these are very important. And so what this is saying is, and we're going to jump ahead a little bit to the Bohr model, but we'll see that what this was saying is that if we have energy levels, so let's say we have the energy level here and here, energy level 2. So if we have our energy level state and we excite it, we put in a lot of energy, we can excite our atom to an excited state. But there was no in between, so you could not go halfway between the two energy levels. It was like a ladder. You can only go from one step to the other. There was no step in between. And so that this delta E could only happen in steps. And so this was idea of quantization, meaning that you could have quantum, like steps of energy, of excitation, but you could not have a continuous, basically you couldn't excite an atom to any energy, only in steps from allowed energy states. Now, what makes an allowed energy state is unique to the atom, and the structure of the atoms would determine the energy distance, so how much energy you'd have to add to get to each step. And so that's why we can actually use the atomic emission spectrum of different elements to identify them. And so we can have the emission spectrum. The absorption spectrum is just the opposite. Imagine a rainbow with black bands. Either one can be used to help identify the presence of elements based on their span, based on the bands that we see. And so you can go online and I post a video that'll show this, how different elements, because they have different energy spacings, it's kind of like a fingerprint, can be used where hydrogen is the simplest. And once you have more electrons in your nucleus, more electrons in your atom, you'll have more bands in your emission spectrum.